Welcome back to the course Modeling Combustion with ANSYS Fluent offered by Adal Systems. So in today's class we will discuss about species transport model. So let's begin the class. Introduction to species transport model. This model is simple and it is widely used for solving reacting flows. The reason is it solves conservative equations of convection, diffusion and reaction sources for each component species. In species transport we can add mixture materials which will specify a set of species to be included in the model. So some of the key features of this model are as follows. Mixing and transport of chemical species can be done using this model. Then various chemical reactions like volumetric, which happens in bulk, volume, then wall surface reaction, particle surface reaction, etc. These reactions can be modeled simultaneously. While defining mixture material, we can add up to 500 different chemical species using this model. One of the most important feature of this model is that turbulence chemistry interaction has been focused and 4 different models have been embedded in species transport. So based on the problem definition, one can go with the turbulence chemistry interaction model. Also, there are some of disadvantages using this model, and they are when mixing and kinetic time scales are comparable, this model becomes unreliable. Also, it is difficult in determining intermediate species and dissociation effects. Now we will see what all are the steps involved when we are dealing with species transport model. So these are some of the steps which we gonna follow, and we will discuss each of them in further slides. So the first step, that is enabling species transport model. After enabling viscous model and energy model, we have to go into species and we have to enable the species transport model. Then we can select what kind of reactions we want to include in our model, and there are other options also one can go through. Next important step is defining the mixture material. Various fuel oxidizer combination mixtures are already embedded in Fluent, which one can go and select. One of the example is methane and air. Select the template and then go on. Otherwise, one can create their own template using different combinations of fuel and oxidizer. So after selecting the flame, next step comes is defining the properties for this mixture and its constituent species. You can individually go and change properties of methane as well as air and for the overall mixture as well. So the third step is to define cell zone conditions and boundary conditions for the species. We have to give boundary conditions for this species. So we have to give mass fraction of fuel as well as mass fraction of oxidizer at all the inlets. For inlets, at what mass fraction of fuel and oxidizer it will be entering the domain in one condition, that is addition of mass fractions of fuel and oxidizer should always be equal to 1. At walls, the default is 0 gradient boundary condition. One can go and change it also according to the problem. And for very small inlet velocities, inlet diffusion can also be defined. Next is defining any other chemical source terms, because there may be a case when species sources exist in your problem but you don't want to model them throughout the mechanism of chemical reaction. So you can add them as source or sink of a chemical species within the computational domain using this option. So next it comes to fifth step, that is solution procedure. So while dealing with combustion problem, there may arise some difficulties because many species and chemical reactions are involved when we are dealing with a combustion problem. So there will be a stability and convergence problem. So some solution procedures they involved by changing some of the under relaxation factors. One step which many of the people follow is two-step solution procedure, that is without energy equation, cold flow analysis will be done, then continuing the same simulation, then hot flow analysis will be done with enabling the energy equation. One can vary the density under relaxation factor because when combustion is involved, the local temperature value which it reaches is very high and then it may lead to divergence. At that time one can alter the density under relaxation. Also in a reacting flow, ignition can be defined using batch or a spark model which is already present. So these are some of the solution procedures. After everything is done, post processing has to be done. So for post processing, various mass fraction, mole fraction, molar concentration for each individual species can be calculated and can be seen through various plots, profiles, etc. in ANSYS Fluent. One more thing which we can do is Chemkin is one of the product of ANSYS in which complete chemical kinetic analysis can be done. So one can import their mixture material in Chemkin and carry out the analysis, and then it can be imported back to ANSYS Fluent and a combustion problem can also be solved. So these way species transport model works. So summary of today's class. So we learned that species transport is simple model which is widely used for solving reacting flows because conservative equations of convection, diffusion and reaction species for each components are solved here. Then mixture materials can be added, which is a very good thing. Then we saw some of the key features of the model, that various simultaneous chemical reactions are solved and etc. Also, we saw some of the disadvantages where the model becomes unreliable. Then we saw the steps we can use to model a combustion problem using species transport model. So these are the references for today's class, and next class we will start with non-premixed combustion model. Thank you.